Okay, in our discussion of precipitation reactions, we talked about how to predict what the product of our precipitation reaction will be by using our solubility rules and by separating out the ions of our reactants and predicting the possible products, and then using our solubility rules to predict which, if any, of those products will be insoluble. That is, it will crash out of solution as a precipitate. So when we describe these reactions, we're used to seeing the standard way of doing this by writing a molecular equation, right? So in the case of the case where we had potassium chromate as an aqueous solution reacting with barium nitrate, oops, NO3 2, which is also aqueous. And this goes on to produce the precipitate of barium chromate, which is a solid, and aqueous potassium nitrate. Whoops, we gotta make this a little bit bigger or a little bit smaller, maybe. There we go. Okay, and this is aqueous. So this is what we would call a molecular equation, or it's sort of the standard equation that we've been using so far. Now, in this molecular equation, it's important that we're writing the phases here. That indicates that this is our solid precipitate that is formed, and that this is a precipitation reaction. Now remember, whenever we write these aqueous species, that means that we have all of these ions separated in solution. And in the end, when we have potassium nitrate, these ions are still in solution. Okay, now in our steps towards predicting that this was in fact our precipitate, barium chromate, it was useful for us to write out the ions as they exist in solution. That is, they're separate. That is, we can write what we call an ionic equation. Okay, so we are going to separate our ions. We get 2 potassium ions, we get a chromate ion, we get a barium ion, 2+, and 2 nitrate ions. Okay, when we write it out in this way, we then do the same thing on the right-hand side, and we see that barium chromate, because it is a solid, those ions are not separate. And we also have aqueous potassium ions and aqueous nitrate ions. We got 2 of each of these. Okay. So in this full ionic representation, we're really making a special note that these ions that are aqueous are not together in ionic compounds, but rather that they are separate. Okay. Now, when we look at this equation, we see that we start off with all of these ions that are present in solution, and at the end we have a solid product, and we still have these potassium and nitrate ions that are in solution. Now, these potassium and nitrate ions are not actually participating in the chemical reaction. They are what we call spectator ions. So they are present at the beginning initially to balance the charge of their counter ions. So the potassium ions were part of potassium chromate. So as a solid, it's a neutral compound, but when we dissolve it, these ions separate. Now, because the ions are present in the beginning and in the end, they're not actually taking any active role in the reaction itself. And again, we call these spectators. They're just hanging around to watch. It is often useful for us to describe a chemical reaction in terms of the actual chemistry that is occurring. That is to say, we will write a net ionic equation to focus in on what chemistry is actually occurring. And when we do this, we simply omit all of those spectator ions. That is, anything that is present as a reactant and is unchanged as a product, like potassium and nitrate, right? These are not participating, and we basically cancel them out of our equation to get a net ionic equation. So in this particular case, our net ionic equation would simply be aqueous barium ions plus aqueous chromate ions are going to form solid barium chromate. Again, we're really just focusing on what is actually occurring in this chemical reaction. Oh my goodness, go away. Okay, so when we describe these reactions in aqueous solution, we can designate the molecular equation, which shows the formulas of my reactants and products as well as their coefficients. In predicting what a possible solid might be, in the case of potassium chloride reacting with silver nitrate, we get a white precipitate that, using our rules, since potassium nitrate is certainly going to be soluble, we could predict that silver chloride is going to be our product. Now, to get to this prediction, it is often again helpful for us to write out the ionic representation of our reactants and then to imagine what possible products they could form. Okay, and then using our rules, we would be able to predict that this silver chloride is in fact our precipitate in this particular reaction. Once we have identified our reactants and products, we can look at this full ionic equation and recognize that we have potassium ions as a reactant, and these aqueous ions are still present as a product. That is, these potassium ions are spectator ions. We can do the same thing with our nitrates, right? So these also are present both at the beginning and the end, and we can think of an equation much like an algebraic expression where factors that are on both sides of the arrow basically cancel out, and so we can cross out those spectator ions to get to our net ionic equation. In this case, chloride reacts with silver to produce silver chloride.